Now that we've talked about how to define trig functions, I want to focus on how to graph them. So I'm going to focus on the sine graph at first. And I have a little setup here just to remind us what our definitions are. So I am going to be using the unit circle a fair amount and remembering that in the unit circle, we can think of plotting an angle in standard position. We can also think about that angle of pi here, that is in radians. I can also think of that as a length along the uh, circumference of the unit circle. So in general, if I look at an angle in radian measure, if this is alpha, then what's also true with the unit circle, since its radius is 1, then this length is also going to be alpha. It is sometimes helpful to be able to kind of translate between angles and distance along the unit circle. Okay, and in order to get a good graph, we're going to keep in mind here a couple of special right triangles. We have our half square triangle, and we have our half equilateral triangle here. And these are the angle measurements in there and also the side length proportions. So remember in the half square, for example, if we call each leg length A, then the hypotenuse would be square root of 2 times A. And since we are taking ratios for all of these trig functions, when I take the ratio of any two sides, those a's are going to cancel out. So I'm just going to remember them with leg length 1 for simplicity. So let's look at the sine function. And we're going to start at angle 0. And I've made a little table here. And this is basically all of the angles that we should know. We should know how to calculate the all of the trig functions on between 0 and 2 pi. And of course, after 2 pi, it's going to repeat itself. So I'm actually going to start in the unit circle, and I'm going to remind us in looking at the definition of sine, if I'm looking at a right triangle, then the sine of an acute angle is the length of the opposite leg divided by the length of the hypotenuse. And if I'm looking in the unit circle, then if I take an angle, there's alpha, then I find the point on the unit circle with xy coordinates, and that the sine of that angle is just the y coordinate. So I'm actually going to start, in terms of filling out this table, I'm going to start by just filling out the compass points. So starting at an angle of 0, which is at the positive x-axis, I'm looking at the y-coordinate of that point on the unit circle, and that y-coordinate is going to be 0. So I'm going to put that down here. And then the next easy one is looking at when my angle becomes pi over 2. Then the y-coordinate there is 1. So I'm going to put a 1 here. And then when the angle becomes pi, then the y-coordinate of that point is going to be 0. And then when the angle becomes 3 pi over 2, then the y-coordinate is -1. And then when we get all the way back to 2 pi, then the y-coordinate is going to be 0 again. Okay, so I'm going to do that, and I actually have axes set up, and I'm gonna start here, and I am going to label some points. I'm gonna call this pi, and this is going to be 2 pi, and then that makes this pi over 2, and then here's pi is the same as 2 pi over 2, and then here's 3 pi over 2, and then 2 pi is 4 pi over 2, and then I have 5 pi over 2. And I'm going to go ahead and put those points when your angle is 0, that's the y-coordinate is 0. When the angle is pi over 2, the y-coordinate is 1. This should have been a 1. No, minus 1. When the angle is pi, the y-coordinate is 0. When the angle is 3 pi over 2, the y-coordinate is negative 1. And when the angle is 2 pi, the y-coordinate is 0. And then we start to repeat ourselves at 5 pi over 2. That's now here. Then the y-coordinate is going to be 1 again. So here the y-coordinate is going to be 1. Okay. And if we look at kind of traveling around the unit circle and looking at what the y-coordinates are for all of these, basically the y-coordinate goes from 0 to 1, back to 0, back down to negative 1, back to 0, back up to 1, down to 0, down to negative 1. And so my y-coordinates are always going to be between negative 1 and 1, and they're going to be kind of smoothly transitioning between those values, between negative 1 and 1. So my whole graph is going to fit in here, and it is going to kind of look like this smooth wave like this. And we are going to take some time to get more of these points in just for practice of graphing. So before I actually connect those points, I'm going to plot many, many more points. Okay, so maybe the next easy one to do here is the pi over 4s. So the sine of pi over 4, here's, I'm going to look at the special right triangle here. The sine of pi over 4 is opposite over hypotenuse. So that's 1 over square root of 2. So looking here, this is 1 over square root of 2. And if I look at this on the unit circle, I'm going to put my angle there. There's my pi over 4. And here, my y-coordinate, if I look down, if I build my little reference triangle here, then this length should be 1 over square root of 2. And just for reference, 1 divided by the square root of 2 is approximately 0.707. Put that there for reference. Okay. And so then I am actually going to take, for my building my graph, I'm actually going to take this segment here and take a copy of it down for my graph. Because I built my graph with the same scale as this circle. So that means I can use this height here. So this is, I'm just going to put a little reference here. This is 1 over square root of 2. And so now, oops, before I do that, I'm going to find my pi over 4s. So pi over 4 is half of pi over 2. So this is going to be a pi over 4. And then, so here's 1 pi over 4, 2 pi over 4 is pi over 2, and then there's 3 pi over 4. And then 4 pi over 4 is pi, and then 5 pi over 4. And then 6 pi over 4 is the same as 3 pi over 2. And then there's 7 pi over 4. 8 pi over 4 is 2 pi. And then there's going to be 9 pi over 4. And 10 pi over 4, 11 pi over 4. Okay. And so I'm going to take this. Here's my length. This is my y coordinate of at pi over 4, and I'm gonna just kind of put this here, and that actually gives me my height of that point. Okay, and I'm going to look at 3 pi over 4. Let me bring this back. At angle 3 pi over 4, I'm over here. And again, I have that same height. It's a positive 1 over square root of 2, okay, or 0.707. So I'm going to put that here. Now I'm just kind of eyeballing it, making sure that this is the same height. And then at angle 5 pi over 4, let's bring that back here. At angle 5 pi over 4, so let me actually put all of my pi over 4 angles there. Okay, I'm using the grid and the diagonals along the grid. So here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. And if I look at the height, the y coordinate of that point, it's going to be a negative 1 over square root of 2. So I'm going to take this same length, but in the negative direction at 5 pi over 4. So that's where that point is going to be. And then at 7 pi over 4, it's going to be the same height. And then at 9 pi over 4, 9 pi over 4 is coterminal. It ends up in the same ending area as with 1 pi over 4, so it's going to be back up here again. And 11 pi over 4, same. I should also mention I could go into the negative pi over 4 and negative pi over 2. Let's go the negative realm. So negative pi over 4 would be here. And this would be negative pi over 2. The y coordinate at angle negative pi over 4 is going to be negative 1 over root 2. And the y coordinate at negative pi over 2 is going to be negative 1. Okay, so we can see this filling out pretty nicely. Let's look now at the pi over 6 and pi over 3 angles. So one thing that's actually kind of nice about this that I like to use when I'm working with something where I have some precision drawing tools like this, you know, in my tablet, I have a way of making perfect circles. And so I like to make my circles in an even sized radius, where my radius is an even number of grid lengths, because that means in the half equilateral triangle, I know that the shorter side of the triangle is half of the radius or half of the hypotenuse. And so that means I can tell how to make a pi over 6 angle by my radius here is four grid lengths, which I'm calling 1 unit. But that means if I go to this point here where the y coordinate is half of the radius, then if I draw an angle through there, that actually gives me a perfect pi over 6 angle. And then again, for the other direction, if I come here to where my x coordinate is half the radius, my radius is 4 grid lengths, so I'm going to go x coordinate is half of that, two grid lengths. That will give me a perfect pi over 3 angle. When I'm looking at this triangle and trying to figure out the sine of this angle, I could be looking at a reference triangle where I drop a perpendicular inside of the unit circle. But I generally like to use this triangle with the reference sides as 1, 2, and the square root of 3. And so I kind of when I'm doing this, I don't really think about the unit circle as much as I think about just get the angle and then I kind of drop aside and here is length 1, 2, and square root of 3. Okay, where here the y coordinate or the x coordinate is square root of 3 and the y coordinate is 1 and r here is 2. And so in this case, sine of theta is the y coordinate divided by r, and in this case, it would be 1/2. Okay. I am going to erase all that stuff and just kind of keep us anchored on so that this it is also true that like in the unit circle, the y coordinate is just 1/2. So that means the sine of pi over 6 is 1/2. And then the sine of 2 pi over 6, which is pi over 3, here I'm looking at the half equilateral triangle. And instead of my angle being the smaller angle, my angle is the larger angle. And so the sine of that is going to be root 3 over 2. And by the way, that is approximately 0.866. Okay. And now then when I come through here and take 2 pi over 3, then the y coordinate is still going to be root 3 over 2. And then when I come to 5 pi over 6, the y coordinate here is going to be 1/2 again. And then when I get to angle of 7 pi over 6 here, my y coordinate is going to go negative. My y coordinate is going to be negative 1/2. All right. And then at angle 8 pi over 6, which is the same as 4 pi over 3, the y coordinate is going to be negative root 3 over 2. Okay, so let's fill those numbers in. At 2 pi over 3, the sine of 2 pi over 3 is going to be again root 3 over 2. And then, oops, where did my 3 pi over 4 go? Oh, 3 pi over 4, I went 1. This was supposed to be 1 over root 2. 5 pi over 4, it should be negative 1 over root 2. And at 7 pi over 4, it should be negative 1 over root 2. Where am I? 5 pi over 6. My y coordinate should be 1/2. 7 pi over 6, y coordinate is negative 1/2. And then at 4 pi over 3, my y coordinate is negative root 3 over 2. And at 5 pi over 3, that's here. And my y coordinate is going to be negative root 3 over 2. And then at 11 pi over 6, that's there. And my y coordinate is going to be negative 1/2. Okay. I'm going to get rid of all of this stuff and I'm going to grab pi over 3 angle and a root 3 over 2 height. Actually, let me just grab the root 3 over 2 height when the x coordinate is 1/2. Okay, putting these pieces together. All of these tick marks might start looking very confusing, and I want to kind of point out here is pi. Okay, let's for the moment, can we ignore the pi over 2 and the 3 pi over 4 and the pi over 4? And I want to think about taking this length pi and divided it into 3 equal pieces. So those are going to be the green pieces. So this is going to be pi over 3, and then 2 pi over 3, and then there's pi is 3 pi over 3, and then the next green piece is 4 pi over 3, and 5 pi over 3, and then 2 pi is 6 pi over 3, and then the next green piece is 7 pi over 3, and then 8 pi over 3. Okay, and likewise going backwards, this is going to be negative pi over 3. Again, looking at that pi, if we could ignore the black lines, the pi over 4s and the pi over 2s, half of pi over 3 is pi over 6. So this would be pi over 6 here. And then 2 pi over 6 is pi over 3, 3 pi over 6 is pi over 2, 4 pi over 6 is 2 pi over 3, and then there's 5 pi over 6. And then 6 pi over 6 is pi, 7 pi over 6. 8 pi over 6 is the same as 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. And then I have 11 pi over 6. And then 2 pi is 12 pi over 6. Then there's 13 pi over 6. 14 pi over 6, 15 pi over 6, 16 pi over 6, 17 pi over 6. Okay, back in the negatives, here's negative pi over 6. All right. This is sorting out axes. Now, at pi over 6, my y-coordinate is 1/2. So pi over 6, my 1 unit is 4 grid lengths, and so I'm going 2 grid lengths up. And then at pi over 3, my y-coordinate is √3/2, and I am just going to actually take a copy of that height here so I can see where it lands. And then I'm going to copy that height at 2 pi over 3. The sine of 2 pi over 3 is again √3/2. Copying that height. The sine of 5 pi over 6 is 1/2. While we're here, I'm going to fill in the negative ones. Sine of negative pi over 6 is negative 1/2. The sine of negative pi over 3 is going to be negative √3/2. Let's see, that's the sine of 7 pi over 6 is going to be negative 1/2. Sine of 4 pi over 3 is negative √3/2. I'm going to go ahead and just copy that length again. Copy that length, and it's a negative y-coordinate there. 5 pi over 3, y-coordinate is again negative √3/2. Sine of 11 pi over 6 is negative 1/2. And then the sine of 13 pi over 6, that is going to be the terminal side of that angle is in the same place as the terminal side of just regular pi over 6. And copying these lengths again. 8 pi over 3, sine of 8 pi over 3 is √3/2. Sine of 17 pi over 6 is 1/2 again. Okay, now we have lots of points filled in, and you can see this really beautiful curve. And so I am going to fill that in. Drawing smooth curves is difficult. Okay, so this is what the sine graph looks like. This is y equals sine of theta, where my horizontal axis is recording the theta, the angles, and then the vertical axis is recording the sine. And I want to point out this y here is actually different. It's kind of the same here, but it's different from the x and y in this in the unit circle here. Okay. A couple of things. One, this graph repeats itself after 2 pi units. And so we tend often to just sort of kind of focus on graphing the fundamental period between 0 and 2 pi. Also, the sine function does have a symmetry across the origin. So the sine function is odd, which means that the sine of, if I take the negative of the input, that gives me the negative of the output of the original. Okay, and I do actually want to take a moment here to look at, I built a different graph or a dynamic graph, which has basically all of that same stuff that I drew, but faster. So I wanted to take the time to draw all of these things by hand and go the slow route. But I want to show you what it looks like kind of zooming out and looking at all of the pieces together. So here I have the unit circle again, and as I'm thinking about an angles in this particular drawing, I really want to think about the angle not as the so I don't want to be thinking about necessarily the angle, but I want to be thinking about this length along the circumference of the circle. It's the same thing. So if I were to draw the angle from the origin out to this point, that angle would have a radian measure of beta. And in the unit circle, that's also the length of this arc. In terms of this particular dynamic model, it's just a little bit easier to draw it with this being the side length. And then I'm also going to see, I'm going to be looking at that side length. This is exactly the same side length that I'm going to be plotting on the horizontal axis in my graph. Okay, so you can see this arc length is the same as this straight length. And if I increase my beta, then that increases. So this straight length is the same as this arc length. And now I'm just going to take that unit circle out of the picture so I can see the graph. Now if I look at the sine of the angle, in each of these instances, the sine of beta is just going to be the y coordinate. So as I start at beta equals 0, the y coordinate is 0. And then as I increase, you can see the running y coordinate here. The y coordinate is becoming bigger, and it reaches its max of 1 when beta is pi over 2. So here at beta is pi over 2, that's the max sine value. Yeah. And then the y coordinate is going to go back down to 0, and it's going to then go to -1 and then up to 0. And it's going to repeat itself if I keep going around the circle. And now I've gone around the circle 2 times. So I've gone a total distance of 4 pi around. The point on that horizontal axis is out of the screen and we can't see it right now. So let me bring that back. Okay. And I'm going to show on the graph. So this length here is the same as this length here. Okay, this is the same y coordinate. And now as I start out, the sine of beta is 0, the sine of 0 is 0, and then as I increase beta, my y coordinate increases, and then it maxes out when beta equals pi over 2, and then sine of pi over 2 is 1, and then it comes back down, and then at beta equals pi, the sine of pi is 0, and then as I continue for beta a little bit bigger than pi, the y coordinate here is going to be negative, so I'm going to be plotting a negative value. So this is what it looks like. Okay, and then here I start repeating again. I've gone a full circle, so my y coordinates are going to start repeating themselves again. And also, of course, if I go in the negative direction, it's going to continue that curve on the left side of that graph too. This was very detailed. I'm going to go into the graphs of the other trig functions in less detail in the next video.